Welcome to the Tech Room, your weekly breakdown of semiconductors, AI, and gaming. I'm Jess.
And I'm Mark. This is the podcast brought to you by SBN Media Studio.
Today on the show, we have a packed agenda. In semiconductors, the Angstrom era arrives as 2-nanometer chips hit mass production. In AI, a historic DRAM apocalypse is sending memory prices into the stratosphere. And we'll look at how the sheer cost of AI hardware is completely reshaping the global map.
The thread connecting it all this week, the semiconductor industry is entering a definitive, capital-intensive era. Let's dive in.
So, Mark, I want you to think about, the most expensive physical object you can actually hold in your hands.
Oh, man. Probably a gold bar or, I don't know, a really rare diamond or something.
Right, that's what most people would picture. But try a 12-inch disc of highly purified silicon that currently costs around $30,000.
Wow.
Yeah, and that is the baseline reality we're stepping into today. Because the industry has officially crossed into the Angstrom era. Right. The logic chips, the foundational brains powering this whole artificial intelligence boom, they've actually crossed the 2-nanometer threshold into high-volume manufacturing. And the underlying physics of how we even got here is just completely wild.
It is. And, just the speed of this transition is really what should be catching everyone's attention right now. Because based on official company filings, this is Tier 1 data coming directly from the source, TSMC has already entered mass production for its N2 process.
So they're actually rolling them out.
Yeah. They're running this out of their Fab 20 in Baoshan and that accelerated facility they have down in Kaohsiung. But the metric that actually matters here is the yield.
Right. How many chips actually work?
Exactly.
Yeah.
And they were reporting 70 to 80% yields right out of the gate.
Wait, 70 to 80% on a brand new node?
Yeah. For a bleeding-edge lithography node, hitting that kind of efficiency in the first wave of production is, frankly, absurd. It means they've somehow mastered the sheer complexity of extreme ultraviolet or EUV multi-patterning way faster than anyone modeled.
That's incredible. But we really shouldn't overlook Samsung in this race either.
True.
Because according to their latest performance review, they just hit a 70% yield milestone on their SF2P node, which is their second-generation 2-nanometer process.
Oh, wow. So they're right there with them.
Exactly. And that data point effectively breaks the monopoly we've seen over the last 3 years. The entire AI industry has been completely bottlenecked, basically tethered to whatever capacity TSMC could carve out for them.
Right. Everyone waiting in line.
Yeah. So Samsung proving that they can match those yields at 2-nanometer, it gives players like NVIDIA and Qualcomm a highly viable secondary option to actually scale their hardware.
Which they desperately need.
Yeah.
And, there's also a fundamental shift in the geometry of these chips that makes these yield numbers so impressive. We are officially witnessing the death of the FinFET transistor.
The end of an era.
It really is. For a decade, FinFET was the industry standard. For the listener, you can sort of picture it like a toll booth with barriers on 3 sides of a road. It worked perfectly for regulating the flow of electrons. But when you shrink that road down to 2 nanometers...
Which is literally the width of just a few atoms.
Right, exactly. When you get that small, the physics of the universe start working against you. You get this phenomenon called quantum tunneling.
The electrons just bypass the gate.
Yeah. The barrier is so incredibly thin that electrons essentially teleport right through it, even when the gate is theoretically closed.
Which translates to massive energy leakage.
Yep.
And when you're building an AI data center with, 100,000 GPUs, power leakage doesn't just mean a slightly higher electric bill. It means the server rack literally melts.
Right, exactly.
Yeah.
That physical constraint is exactly why the whole industry is shifting to gate-all-around, or GAA, architecture.
Oh.
So instead of a 3-sided toll booth, GAA wraps the gate entirely around the channel. It becomes a fully enclosed tunnel. So you dictate exactly how many electrons pass through, giving you absolute control over power efficiency.
And Intel is doing something really interesting here too, right?
Yeah. Intel is pairing their version of this, which they call RibbonFET, with another breakthrough called PowerVia. In a traditional chip, the power delivery wiring and the data communication wiring, they're all tangled together on the front of the silicon.
Which creates massive microscopic traffic jams.
Exactly. So PowerVia takes the entire electrical grid and just buries it on the back of the chip. That leaves the front entirely dedicated to logic and data.
That's a brilliant piece of engineering.
It really is. And official announcements confirm Intel's 18A node using this tech has just entered high-volume manufacturing.
I mean, the engineering is undeniably miraculous, Mark, but we really have to look at the brutal business math here.
Oh, costs, yeah.
Yeah. You have TSMC charging roughly 30 grand for a single 2-nanometer wafer. When the toll to get onto the highway is that exorbitant, the pool of companies that can actually afford to design and manufacture these chips shrinks down to just a handful of $2 trillion hyperscalers.
Yeah, the barrier to entry is insane.
Apple and NVIDIA are basically buying out the VIP section, leaving the rest of the industry scrambling for legacy capacity.
Well, and that staggering price tag, it's the direct byproduct of the equipment required to build an enclosed tunnel at the atomic scale.
Right, the ASML machines.
Exactly.
Yeah.
ASML, the Dutch firm that manufactures lithography tools, recently shipped their first high-NA EUV machine to Intel. Just this piece of equipment is the size of a double-decker bus.
Wow.
It uses lasers to vaporize droplets of tin to create extreme ultraviolet light, and it costs upwards of $350 million.
For one machine.
One machine. And a modern fab needs dozens of them. Foundries are absorbing billions in capital expenditures before a single chip is even printed. They have no choice but to pass that cost down the chain.
And we're already seeing the ripple effects of those capital expenditures in the supply chain data. Like, according to Tier 1 and Tier 2 supply chain reporting from DigiTimes, TSMC is planning to raise prices by 5 to 10% across all its advanced nodes in 2026 just to offset these equipment costs.
Which is a huge jump at those price points.
Exactly. And that massive capital requirement completely changes how nations view semiconductor manufacturing. It's no longer just a tech sector issue. A fab is now considered critical national defense infrastructure.
Right, which explains the massive capital consolidation we're tracking this week. Take Intel's footprint in Europe, for example. Evertick reported that Intel is spending $14.2 billion to repurchase the 49% equity stake in its Irish Fab 34 facility from Apollo Global Management.
Which makes total sense.
Yeah. I mean, when you're ramping up a sovereign 1.8 nanometer node, you cannot afford to have a private equity partner dictating your capital expenditure schedules. You need absolute, uncompromised control over your manufacturing floor.
It's a global race to secure physical capacity right now. The U.S. and Taiwan are striking deals for hundreds of billions in manufacturing commitments. We see TSMC filing plans with the Taiwanese government to launch a second 3-nanometer plant in Japan by 2028.
Oh yeah, the Japan expansion is huge.
And it isn't just the established players either. Evertick also reported that India just approved $750 million in new electronic manufacturing incentive. They are actively trying to capture the spillover from this high-cost foundry war. I mean, they're aiming to quadruple their electronics output to $500 billion by 2031.
That's ambitious. But, building the logic chip is really only half the battle. You can manufacture the fastest 2-nanometer AI brain in the world, but it is completely useless if it's starved for data.
Oh, absolutely. The bottleneck shifts.
Yeah, and that physical limitation leads us directly into what analysts are calling the DRAM apocalypse.
I love that term.
It's terrifying, but accurate. The AI industry's insatiable hunger for data bandwidth is triggering a structural crisis in the memory market.
So to understand why memory prices are surging, you really have to look at how artificial intelligence actually computes. An AI model requires thousands of gigabytes of data to be pushed into the processor simultaneously. Traditional memory, which just sits flat on a motherboard a few inches away from the processor, it simply cannot move data fast enough. The travel time literally creates a bottleneck. So the solution is high bandwidth memory, specifically the new HBM4 standard.
Right, and HBM4 requires a radically different manufacturing philosophy. Like, standard memory is like a sprawling one-story suburban neighborhood.
Okay, I like this analogy.
High bandwidth memory is a dense 12-story skyscraper. Foundries stack memory chips directly on top of each other, and they connect them by drilling microscopic vertical tunnels through the silicon called through-silicon vias.
Wow.
They then place this entire skyscraper on the exact same package as the AI logic chip. So the data doesn't have to travel across motherboard. It just takes a high-speed elevator straight down into the processor.
That's brilliant. But building skyscrapers requires significantly more raw material and precision than building suburbs. A single defect in just one layer of that HBM stack means you have to throw the entire skyscraper away.
Exactly, which is brutal for yields.
Yeah, it creates what TrendForce calls a wafer penalty. The big three memory makers, Samsung, Micron, and SK Hynix, are pivoting all their physical foundry space to manufacture this ultra-high margin HBM4 just to feed NVIDIA's next-generation architecture. I mean, Micron's entire 2026 supply is already completely sold out.
Yeah, which is just wild. And because the foundries are pouring all the resources into the HBM4 skyscraper, the supply of traditional flat memory is just plummeting.
The crowding out effect.
Yeah, a classic crowding out effect. TrendForce, which is a top-tier research firm for supply chain dynamics, is projecting a staggering 90 to 95% quarter-over-quarter jump in standard server DRAM prices.
90% in one quarter.
Yeah, and mainstream NAND storage prices have already surged nearly 65%. The economics of IT infrastructure are just being violently rewritten.
Seriously, if you're managing a technology budget right now, the downstream effects of this are alarming. Let's say you run a hospital network, right? Managing patient databases, or maybe a logistics company tracking global shipping.
Yeah, regular enterprise stuff.
Exactly. You have absolutely zero need for a $30,000 AI accelerator. You just need standard server memory. But because the major cloud providers are locking up all the silicon to train generative AI, your basic infrastructure costs are effectively doubling overnight.
It's collateral damage.
Totally. We're even seeing enterprise storage companies like Kioxia forming these strategic alliances with pure-play DRAM makers like Nanya Technology, according to Evertick, just to secure baseline inventory.
Well, the sheer cost of AI hardware is driving an absolute boom for the companies designing the chips, while creating a total nightmare for the ones buying them.
Right.
Like a recent TrendForce report showed that global fabless IC firms, companies like NVIDIA and AMD, that design chips but don't manufacture them, they saw 44% year-over-year growth. They capture all the immense margin of the AI boom, while the foundries are left to absorb those $350 million machine costs to actually print the designs.
That divergence between the cost of the hardware and the value it generates has turned compute into a highly liquid, highly volatile financial asset. I mean, we're no longer in an era where startups just buy their own servers.
No, absolutely not.
SemiAnalysis, which is a great Tier 2 research firm, just launched a one-year rental price index specifically for NVIDIA H100 GPUs.
A rental index.
Yes, because the leading-edge hardware is entirely hoarded by giants like Amazon and Microsoft. So transparent rental pricing is now a mandatory metric for any mid-tier lab trying to model their operating costs.
And when a physical object becomes that scarce and that valuable, a gray market inevitably forms around it.
Oh, of course.
Yeah, Reuters, obviously, Tier 1, reporting covered authorities in Singapore charging individuals in an ongoing AI server fraud investigation.
Wow, really?
Yeah, these massive clusters of high-performance GPUs are being treated like bits of gold. They're being diverted, smuggled, and subjected to these complex chain of custody thefts, all because a single pallet of these servers is worth tens of millions of dollars.
But, the extreme bottleneck in manufacturing isn't just about printing the chips, though. Stitching the logic processor and that memory skyscraper together is arguably the hardest part of the process. It requires a technique called advanced packaging, specifically CoWoS, or chip-on-wafer-on-substrate.
Right, and that packaging phase is where the supply chain is heavily constrained right now. TSMC's in-house packaging facilities have been running beyond maximum capacity for over a year.
It's a huge choke point.
Yeah, but we are starting to see the ecosystem broaden to alleviate the pressure. Evertick reported that Camtek just secured a $31 million order from an outsourced assembly and test provider. This equipment is explicitly for inspecting and measuring these complex CoWoS-like advanced packages.
Which is incredibly delicate work.
Oh, yeah. If the microscopic solder bumps connecting the logic chip to the memory stack are misaligned by even a fraction of a millimeter, your $35,000 piece of hardware just becomes a paperweight.
Exactly. And assuming you managed to print the 2-nanometer logic, stack the HBM4 memory, and perfectly package it all together, you immediately hit the next unbreakable barrier.
The power wall.
The power wall. Data centers running these advanced models are drawing so much raw electricity that they're legitimately destabilizing local power grids. The physical infrastructure of a server rack simply wasn't designed to handle this level of density.
Right, and the culprit behind that heat isn't just the processors themselves, it's the copper wiring connecting them.
Oh, interesting.
Yeah, for decades we've used copper to move electrical signals across server racks. But pushing massive amounts of data through copper generates intense electrical resistance. And, resistance creates heat. If you try to push the bandwidth required for next-generation AI models through traditional copper interconnects, the metal will literally melt.
So the solution is to just abandon electricity for data transfer entirely and switch to light. Evertick actually covered a major announcement from Lumentum, a leader in optical networking. They're expanding a massive new U.S. manufacturing facility in Greensboro, North Carolina, entirely dedicated to silicon photonics.
That's a huge deal.
It is. This technology integrates microscopic fiber optic networks directly into the silicon package. So instead of pushing electrons through hot copper wire, you are pulsing lasers. The energy required to move a bit of data drops exponentially, and the heat generation is practically zero.
Silicon photonics is really the only viable path forward to prevent these gigawatt AI data centers from bankrupting municipal power grids. I mean, the transition from electrons to photons at the chip level is just as critical as the transition from FinFET to gate all-around. Every single architectural change right now is driven by the desperate need to increase bandwidth while artificially suppressing power consumption.
Though some argue that the ultimate release valve for this cloud compute bottleneck is going to be edge AI.
Yeah, that's a big debate right now.
The theory is that if TSMC and Intel can shrink these incredibly powerful 2-nanometer nodes down and put them into smartphones and laptops, developers can just run generative AI models locally. You bypass the cloud rental fees entirely, you bypass the data center power grid constraints, and you eliminate the latency of sending data back and forth to a server.
It sounds great in theory, but the debate raging in the engineering community right now is whether the language models are growing in complexity faster than our ability to shrink the hardware.
That's a fair point.
Like, a locally run model on a phone provides incredible privacy and zero latency, sure, but it will always be mathematically inferior to a massive foundational model running on 100,000 stacked GPUs. The exorbitant cost of cloud compute is undoubtedly a massive catalyst for edge computing, but the heavy lifting, the actual training of these systems, will remain permanently locked behind that multi-billion-dollar capital wall.
Okay, let's pull all of this together. If you look at the connective tissue between the TSMC yields, the ASML equipment costs, the dreampocalypse, and the massive sovereign investments in fabs, a very clear picture emerges. The technology sector has entered a definitive, undeniable, capital-intensive supercycle.
Yeah, it really has. I mean, for the last 20 years, the prevailing narrative of the tech industry was defined by software. The barrier to entry was practically non-existent. A couple of developers with a laptop could write a disruptive piece of code in a garage and scale it globally using cheap, easily accessible cloud infrastructure.
Right.
That era of low-overhead innovation is effectively over.
Exactly. The physical reality of the artificial intelligence boom demands hardware that defies comprehension. It requires $350 million extreme ultraviolet machines firing lasers at vaporized tin. It requires $30,000 silicon wafers. It forces the entire global memory supply chain to realign itself around high-bandwidth 3D skyscrapers, squeezing out everyday consumer electronics.
It's totally unprecedented.
The infrastructure required to compete in this space has elevated from corporate budgets to sovereign wealth levels. You are either a nation-state building heavily subsidized domestic fabs, a $2 trillion hyperscaler buying up the entire supply chain, or you are simply a tenant renting time on someone else's hardware.
It fundamentally reshapes the global hierarchy of innovation. When the foundational technology required to participate in the next generation of computing costs billions of dollars just to assemble, it locks out an entire tier of traditional market disruptors.
The toll booth to the future of technology has never been more expensive. It leaves us with a critical question to consider as we close out today's deep dive. In a world where compute is hoarded like gold and basic memory costs are doubling, how does the independent innovator even survive?
It's going to be tough. Next week, I am going to be watching TSMC's manufacturing reports closely to see if they can maintain those 70 to 80% yields as they scale up the Kaohsiung facility. If they avoid the typical defect spikes that plague high-volume manufacturing, the rollout of these next-generation AI accelerators can hit the market much faster than the conservative estimates suggest.
And I will be closely monitoring the memory spot markets. With the HBM4 squeeze in full effect, I really want to track exactly when these 90% server memory contract hikes start actively bleeding into the retail prices of consumer hardware. If you're planning to buy a laptop or upgrade a server rack anytime soon, the window for cheap memory is closing rapidly. That's your Tech Room for this week. I'm Jess.
And I'm Mark. This podcast is produced by SBN Media Studio. Subscribe, leave a review, and we'll see you next Sunday.